Welcome back, everybody. Today we're going to finish up our lesson using the chain rule to find derivatives. Okay, we gave you the basics of the chain rule in part 1. On part 2 we're going to extend things and just look at some uglier problems basically, okay, that utilize the chain rule. Alright, problem 3, extending the chain rule. We want to find dy over dx of this guy here. Now before we start thinking about derivatives, let's rewrite this in maybe a more derivative-friendly form. Sine to the third, I'm going to rewrite that as parenthesis sine of 7x, okay, all to the third here. And why we're going to say this is an extension of the chain rule is when I think about this one, how many functions do I have? Well, I have x to the third on the outside, and within that I have a sine of x. And then within the sine I have a 7x. So really what this problem is a composition of 3 functions. And the trick is with something more complicated than our basic f composed of g, our simple rule falls apart a little bit here, because as far as which one's f, which one's g, is there an h as well? Okay, so let's take a look at how to deal with this. Alright, so we can say that y prime is equal to, I'm just going to think about in terms of outer and inner function. So if I'm starting off with this sine 7x all raised to the third power, my inner function is just everything I'm raising to the third. Okay, so let's take the derivative of the outside, okay, x to the third essentially. That's going to be a 3 times parenthesis squared using my power rule. And then I'm going to put that inner function in its entirety back in here. And then from there what we have is we have the derivative of the inner function. So for now I'm just going to rewrite that as d over dx of that sine of 7x. Okay, I'm going to break this into 2 different parts here. Alright. So we've got our first derivative taken care of. Now we're going to have to use the chain rule again for the next derivative. So we'll just rewrite the first part. 3 parenthesis sine of 7x squared. Okay, so now let's apply our chain rule again for this derivative. Okay, outer function is a sine x. Derivative of sine x is just cosine x. Cosine of x, but instead of x we'll place the inner function inside the cosine, and then that'll be multiplied by the derivative of the inner function 7x, derivative of 7x is just a 7. Alright, so now my derivative's all done. I can combine my constants with multiplication. 3 times 7 is going to be a 21. And then as far as order goes for writing the rest of it, there's no magic way to do it. We could say sine squared of 7x times cosine of 7x. Alright, so there's an example of extending the chain rule, using it twice in the same derivative. Okay, for finding the derivative of a function that's a composition of 3 or more functions. Alright, part B is the same idea. Why don't you pause the video, give part B a shot here, and then like usual hit play to check your answer. Alright, the next set of problems we're going to look at is going to be combining the chain rule with our product and quotient rules. Okay, this one here, part A, looks like we have a quotient rule happening within the product rule because we have a fraction, we have division of 2 polynomials. Alright, first step for this guy though, I'm going to rewrite my function in terms of something I can apply my power rule to. So let's rewrite this all as 2x minus 2 over 3x plus 7, all raised to the 1/2 power instead of with the square root. All right, so now I'm ready to start taking my derivative. We want the derivative of the outer function, which is the square root, or the to the 1/2 power. Okay, that's just going to be a 1/2. Okay, times all of this raised to the 1/2 minus 1 will be a negative 1/2 power. And in the middle here, I just have my inner function. Okay, this same 2x minus 2 over 3x plus 7. So there's my derivative of the outer with the normal inner function on the inside. And then from there, what I need to do is multiply that by the derivative of the inner. Just like we did in the last problem, I'm going to break this down into multiple steps. So here we just have to take d over dx of 2x minus 2 divided by 3x plus 7. All right, I don't have to break this up into multiple steps, but it's helpful to do that sometimes. Okay, we'll leave the first part of the derivative alone. And now I'm just going to focus on finding the derivative of this quotient. Okay, once again, that's just utilizing my quotient rule. So d over dx of f of x divided by g of x, remember, is equal to g of x times f prime of x minus f of x times g prime of x, all divided by g of x squared. Okay, so really at this point, I'm just doing a type of question that we would have had on our last unit test. Okay, so let's go ahead and do that. We'll make a big fraction. We can extend it if we need to. Okay, we've got the denominator here, 3x plus 7, which I'll throw in parentheses. Okay, times the derivative of the numerator. Derivative of 2x minus 2 is just going to be a 2. All right, minus the numerator, that 2x minus 2. Okay, times the derivative of the denominator. Derivative of 3x plus 7 is just a 3. Okay, all over 3x plus 7 squared. All right, so there's my derivative. Now, if the goal of this question was to find the derivative at a specific x value, we could just quit here and plug the x's in. But since we're looking for dy over dx, let's go ahead and clean this up, combine our like terms, see if we can't simplify it a little bit. All right, so the calculus is done. Now we're just on to algebra. I'm going to leave this as 3 separate fractions being multiplied for now, so let's just leave this as a 1/2 here. All right, times now this 2x minus 2 divided by 3x plus 7, all raised to the negative 1/2 power. Let's separate that into 2 separate powers. So let's call that a 2x minus 2 to the negative 1/2 on top over 3x plus 7 to the negative 1/2 on bottom. All right, then times, here we've got a 2 times the 3x plus 7, so we'll call that a 6x plus 14. And then minus, we've got a negative 2x times 3, we'll take care of that one step, minus 6x. And then negative times negative 2 would be a plus 2 times 3 would be plus 6. Still over the same 3x plus 7 squared. Okay, usually we're not going to distribute that out. We'll just leave it in factored form. All right, and continuing, same thing. I'm just going to leave this as 3 fractions, keep cleaning it up. So I've got my half. Okay, times, now if both the numerator and denominator are raised to negative exponents, I can just flip these guys upside down. So we can say this is a 3x plus 7 to the positive 1/2 over 2x minus 2 to the positive 1/2. All right, times numerator here, 6x and negative 6x will cancel. I can combine the 14 and the 6. So that'll be a 20 over 3x plus 7, still squared. All right, so things are getting a little nicer. Let's try to finish it up in this next step or two. So as far as putting everything together goes, we can take care of our constants. Okay, the 2 and the 20 will cancel to turn into just a 10 on top. And then the next thing I can do is notice I've got factors of 3x plus 7 on top and bottom. What I can do is I can combine their exponents. And when you're doing division with exponents, remember subtract. So if I have 1/2 minus 2, what that's going to be is a negative 3/2. So I could combine these two factors here as just a 3x plus 7 to the 3/2 on bottom. And then we still have the 2x minus 2 to the 1/2 power here. All right, so I'm going to say that's about as kind of cleaned up as I need to make this one. Now I suppose the other thing I could do is I could rewrite it in square root form. So that'll just be a 10 over the square root of 3x plus 7 to the 3rd power for that 3/2 exponent times square root of 2x minus 2. Okay, I'd say both about equally as simple. AP exam time, multiple choice answers. Okay, you can see either one of those. But yep, either way there's our derivative, okay, using the quotient rule inside of the chain rule. Next one we're going to take a look at involves the product rule. Okay, part A had the quotient rule happening within the chain rule. Here what I'm going to have is the chain rule happening within the product rule. All right, so let's show you what we mean. We know we're going to have chain rule happening because I have the square root of another function. Okay, square root, we've dealt with a bunch of the examples with that already. Product rule, because I have two functions getting multiplied, I've got a 5x times that square root of 25 minus x squared. So just a reminder, with the product rule, that was d over dx of f of x times g of x was equal to, we could say, f of x times g prime of x plus g of x times f prime of x. All right, so let's go ahead and start writing out the product rule here. We've got, we could say y prime is equal to the normal first function, the normal f of x, which we can say is just the 5x, okay, times then the derivative of g of x. So what I could do is I could take this derivative right away here, applying the chain rule in one step. But once again, what I'm going to do is I'm going to just write that as d over dx of this function. Again, I'm going to write that in kind of ready to find the derivative form. We'll call that a 25 minus x squared to the 1/2 power. Okay, so I could take care of that right away, but what I'm doing here is I'm just going to save it for later, save it for the next step. Okay, continuing with the product rule, we have plus the normal g of x. So that'll just be square root of 25 minus x squared times the derivative of my f of x, which is that 5x. So that'll just be a 5 right here. All right, so essentially, again, what we did is we applied the product rule. We just said, let's take care of this derivative in the next step. All right, so we've got y prime is equal to the same 5x. And now let's take the derivative of this guy here. Okay, we're to the half power again, so derivative is going to be 1/2 to the negative 1/2. Okay, 1/2 times raised to the negative 1/2 power of the inner function, which is my 25 minus x squared. And then times the derivative of that inner function here. 25 is nothing. Minus x squared will be a minus 2x. Suppose we'll close this first parenthesis off. Okay, so there's my d over dx of that square root 25 minus x squared. Rest of the derivatives just the same thing we had before. And there you go. There's a way we could write the derivative expression or function. Okay, but again, multiple choice time, we probably want to clean that up. We call this y primes equal to, let's see here, 5 times negative 2, sorry, 5x times negative 2x, we call a negative 10x squared. So I've got the 5, I've got the negative 2x taken care of. Here we're going to have a 2 on the bottom, and we'll say square root 25 minus x squared on the bottom as well, to the negative power. All right, plus a, we could say just 5 square root 25 minus x squared. And I suppose what we could do here with the 10 and the 2, I'm going to take care of those in line, those will reduce down. And leave me with just a 5x squared. Okay, so we've got our like terms combined, we've got the multiplication taken care of. Now the other thing we might want to do with one like this is actually combine these two fractions here. Okay, so what I do is I need a common denominator. My first fraction has a denominator of square root 25 minus x squared. I can think of this 5 times square root 25x squared as over 1. So we can multiply by a square root 25 minus x squared over square root 25 minus x squared. That's going to give us our common denominator. And then from here what I'll do is I'll just combine all the like terms, combine everything in the numerator. So we've got that minus 5x squared, and then we have plus 5 times. Remember, when I take a square root of something and multiply it by itself, that's essentially squaring. That's going to cancel out your square root. So we can say parenthesis 25 minus x squared. And then cleaning that up, we have y primes equal to negative 5x squared minus another negative 5x squared, just be a negative 10x squared. Okay, plus 5 times 25 is 125. All right, then all divided by the square root of 25 minus x squared here. Okay, so there we go. There's my derivative function, all cleaned up. Once again, there's an example of using the chain rule within the product rule. All right, and the last thing we're going to look at, problem 5. I feel like my last slide might have said problem 5 as well. Whoops. Okay, is using the chain rule with other representations. Okay, so as opposed to just applying the chain rule analytically to equations, we also want to be able to apply it to numerical values in the form of tables, okay, or even graphs. Okay, just like with every derivative rule we looked at, we'll throw a few problems at you where here's the information in the table, can you still apply that chain rule? Okay, so here it looks like we have a table of values for f, f prime, g, and g prime for a few different x values. Okay, we have f of x equal to f of g of x. We want to find f prime of 1. Okay, well, let's start off by finding f prime of just the x. Well, here, f composed of g, that's just our chain rule. That's going to be equal to f prime of g of x times g prime of x. So meaning that if I want f prime of 1, what I'll do is I'll just take this derivative function here and plug in 1s for the x's. So we have f prime of g of 1 times g prime of 1. All right, evaluating that, this is going to take 2 steps to do. Could do it all in your head in 1 step, but not sure I'll work for notes. First thing I need to do is figure out just what g of 1 is before I plug it into the f prime. So we've got f prime of g of 1, my table says that's equal to a 2. Okay, times g prime of 1, we know that right off the bat, that's 5. So we have here then is f prime of 1 is equal to then little f prime of 2, which will be a 4/3 times the 5 again. So we end up with a 4 times 5 would be a 20 square root 3. Let's go ahead and look at one more problem together before we give you one to try on your own. Again, we're talking about chain rule using multiple representations. This time I've got a g of x coming from my table once again, but also part of my function h of x is written out explicitly as e to a power. All right, so first thing let's do is let's find h prime of x. That's going to be equal to the derivative of my outer function, which is e to the x. Okay, with the inner function just placed inside. So that's just going to be e to the g of x once again. Okay, remember, derivative of e to the x is just e to the x. Okay, times the derivative of the inner function, which is g of x. So we'll just write that as g prime of x. All right, so there's my derivative function. Part of it I know explicitly, the e part of it. And then the other part is g. G is some other function where we have the function, its derivative. Okay, since we don't know what that function is, this is all the kind of nicer we can simplify that down to. Which is okay because we want h prime of 1, which will just be substituting the 1 in for the x's. So we have e to the g of 1 times g prime of 1. So that'll be h prime of 1's equal to e to the g of 1 is just a 2. So e squared. Okay, times g prime of 1, which is a 5 once again. All right, that's it. I suppose if this was on a calculator portion, I could round that answer. But if we want to leave it in exact form, I suppose 5e squared looks a little nicer than e squared times 5. All right, there is a part C for this problem, so like usual, take a minute, pause the video, work through that one, and then hit play to check your answer. All right, so that's it for part 2 of the chain rule, okay, kind of the more advanced cases. So now, like usual, get going on the homework. You should be able to complete that whole assignment. Okay, do the best you can with it, and make sure you're asking for help with anything you're getting stuck on. We'll see you next time.